The next presentation is from Professor Simate from here at Wits on carbon nanotubes as heterogeneous coagulants and flocculants for wastewater treatment. Jeff, are we ready?
Okay. Good afternoon, South Africa, or rather good morning, South Africa. I believe you can hear me.
Yes, we can hear you perfectly.
And good afternoon, India. I think first and foremost, let me thank Prof. Majozi for inviting me to be part of this workshop. What I'm going to do is basically just to share results of a study that I was involved in a couple of years ago. That actually looked at assessing the feasibility of using carbon nanomaterials as coagulants. This particular research, or rather presentation, is a basic research, unlike what the previous speakers have talked about. They were basically looking at applied research. Mine is basic research. It was done a couple of years ago. Okay, so in this particular presentation, what I'll do is just give you a brief introduction, and also give you some background on the production and characterization of carbon nanotubes. This background is just to maybe just to excite people who might be interested in pursuing studies in the use of carbon nanotubes, or maybe even its production. Thereafter, I'll deal with the objective of our study, which was to assess the feasibility of carbon nanotubes on as coagulants. So let me start by saying that the search for new and advanced materials for various applications, including environmental protection, is an ongoing and important task of research by many scientists. And what we notice is, as for carbon materials, what is known is that although various carbon materials, including graphite, diamond, and so on and so forth, have been studied and developed and produced previously. It was only in 1991 when a Japanese scientist actually observed for the first time tubular nanomaterials. And these were actually named as carbon nanotubes. In fact, in that particular study, what was discovered was actually multi-walled carbon nanotubes. But a couple of years later, various other researchers also discovered some other types of carbon nanomaterials. So what you actually see in this figure is just that these carbon nanomaterials are actually a graphene sheet. They are more or less like represented by a graphene sheet. If you look at a graphene sheet and if you fold it, then you make some tubes. So you've got a graphene sheet. When you fold it, you make tubes. And that's a graphical representation of carbon nanotubes. And what you see here is basically a single carbon nanotube. You see it's some sort of, it has only a single tube, whereas this one is a multi-walled carbon nanotube, where you have various tubes within a tube. Okay, so these are basically the two types of carbon nanomaterials that are available at the moment. These particular materials actually could either be metallic or semi-metallic, depending on how they are rolled. This graphene sheet has been rolled. But what we also observe is that despite these materials being metallic, they also possess other other properties that have actually rendered them to be quite attractive for a whole range of applications, including water treatment, medical, and so on and so forth. And I think an important property of them that have actually rendered them to be used in water treatment is that they've got specific or large specific surface area. They are hollow and also they have layered structures. But what we should also notice here is that these materials can actually be sort of modified depending on the application that one wants. They can be functionalized, and also because they put some caps at the ends, those caps can be opened up, and so on and so forth. So based on that, what we also notice is at the moment, we have quite expensive conventional and other methodologies that are used for the water treatment. So the view for this study was to see whether carbon nanotubes could be used for water treatment instead of the currently existing processes, which are quite expensive. But before we looked at that, we also observed that there are also some studies that have been done where carbon nanomaterials have been used as in water treatment, such as nanoadsorbents, nanofilters, and nanomeshes. Yeah, so what we did in our case was, instead of looking at these carbon nanomaterials being used as these existing in these existing applications, we wanted to see if they can be used in other applications for water treatment. And that's when we thought of them, when we looked at them as being used as coagulants. And basically our theory, the theory that was behind this was the fact that if we can allow the carbon nanotubes to adsorb on colloidal particles, then what that means is those colloidal particles, they'll be drawn together, just like what happens in the coagulation and flocculation processes. And that basically will result in what is called bridging flocculation. And at the same time, if these carbon nanotubes could actually adsorb on these colloidal materials, they could render the colloidal materials to be neutralized, because what we see is, especially turbidity, that the materials in water are negatively charged. So if our carbon nanotubes are somehow, let's say, positively charged, and then they adsorb on these particles, then they will be neutralized, and it will be possible for these materials to actually settle, as is the case in these coagulation and flocculation processes where we have sedimentation taking place. So these theories formed the basis of the objective of our study. And in testing these particular theories, those theories that I mentioned earlier on, we actually looked at brewery wastewater. And what we see here is the brewery wastewater itself actually has the zeta potential, which was quite negative. What that means is it contained the negatively charged materials. And in testing this, whether the carbon nanotubes could act as coagulants, we looked at one parameter, which was the turbidity. What you see is in most water treatment processes, turbidity is actually used as a measure of whether the treatment process has been effective or not. So that's why we use turbidity as a measure of the flocculation process. I'm not going to go in detail here, but this is the type of equipment that we use to produce the carbon nanomaterials. This is a chemical vapor deposition, and is commonly used for the production of carbon nanomaterials. So after producing the carbon nanomaterials, we were able to functionalize them just to make sure that they are actually indeed carbon nanomaterials using the TEM. As you can see, you can actually see that they look like tubes and fibers. So this is the TEM depiction of our produced carbon nanomaterials. And then we also use the Raman spectroscope. Basically, it was just to determine whether they were multi-walled or single-walled. You can actually see that these are the characteristics of carbon nanomaterials. They've got the G band and D band, but then these were actually multi-walled because they lacked a radio, a RBM peak that could have occurred just before the D band. So because they did not have that RBM peak, we concluded that they were actually multi-walled carbon nanotubes. But what we should also know is it's actually important that these carbon nanomaterials, because when they are produced, they don't have some functional groups on them. So it's important that they are treated so that we embed some functional groups. And based on the fact that our brewery wastewater contained some negative charged materials, so it was important that our carbon nanomaterial tubes were actually functionalized so that they become positive charged. They become positively charged. So, and in so doing, what we did was we used the carbon, or rather we used the hydrochloric acid. And the hydrochloric acid is actually known to be able to impart positive charges on the carbon materials. So that's why we used the hydrochloric acid. And again, what we did was just to sort of characterize our functionalized carbon nanomaterials. So you can actually see that there are some differences between the non-functionalized and the functionalized nanomaterials. And what we also saw is that after the treatment or functionalizing the materials, they actually became more pure than the freshly produced carbon nanomaterials. And that was determined using the TGA. But what we also observed is that the carbon nanomaterials themselves did not actually lose their structure so much. As you can see that they still had the G band and the D band, so they didn't actually lose their structure so much. That functionalization actually, as I stated earlier on, was to sort of like improve them by creating some functional groups that would help in the coagulation process. So you can actually see that the non-functionalized carbon nanomaterials, they were actually quite clean. They were quite clean. They did not have any functional groups on them. Whereas the functionalized carbon nanomaterials, you can actually see the peaks. These are like maybe the oxygen compounds and so on and so forth that were actually introduced on the functionalized carbon nanomaterials. So what we also did was we just wanted to establish, or rather to quantify those functional the functional groups that existed on our carbon nanomaterials after functionalization. Because what we can see, what we notice is they can either be in two forms. They can either be acidic or perhaps maybe basic. But what we saw is as for the functionalized carbon nanomaterial, they had more of basic sites than acidic sites. So what that means is they could actually act as the coagulants for the negatively charged materials in the brewery wastewater. And the other thing that we also observed is after functionalizing them, actually even their surface area became larger than the non-functionalized materials, which was quite good for this particular process. So basically, after that functionalization test, we carried out the coagulation test, but in so doing, we needed to compare the flocculation process with the conventional materials, and we picked ferric chloride as our material to compare with our carbon nanotubes. Ferric chloride, basically, it has some sort of a wider pH range that one can work with, unlike aluminum sulfate. So basically, what we did was just to do the jar test, do the coagulation test and flocculation test. But because our carbon nanotubes, they were not soluble, what happened is we needed to filter the solution afterwards, and measured the turbidity of the solution that we got, and the turbidity actually gave us the turbidity itself was the measure of the coagulation process. So this particular test is where we compared the freshly produced carbon nanotubes, the functionalized ones, and the ferric chloride. But we can actually see that ferric chloride on its own, it was a good coagulant. It reduced the turbidity of the brewery wastewater quite extensively, better than the functionalized carbon nanotubes and the non-functionalized carbon nanotubes. I think the reason here is basically because of different mechanisms that might have been there. For example, if you look at the ferric chloride, some of the mechanisms that are there includes the sweep flocculation, because of the colloids, or rather because of the because ferric chloride actually produces some hydroxides that might have precipitated, such that they carried with them, as they settled down, they carried with them these colloidal materials. So that could be one of the reasons why actually ferric chloride was better than the functionalized carbon nanomaterials, because functionalized carbon nanomaterials, as we observed later, or that the mechanism that is used for coagulation of these colloidal materials was only adsorption and charge dispersion. So having actually, at this particular point, we were certain that at least the carbon nanomaterials, once they functionalized, they could actually act as coagulants. So the next test that we did was just to see the effect of pH and dosage. But before we look at that, what you see here is if you compare the freshly produced carbon nanotubes and the functionalized carbon nanotubes, if you look at the SEM, you can actually see that the functionalized carbon nanomaterials have some sort of colloidal materials on them. They're not as clear as though the pictures, of course, are not very clear, but what you could see here is you can see a lot of black patches on the functionalized carbon nanomaterials, meaning there were a lot of adsorption that took place from the colloidal materials as compared to the pristine carbon nanotubes, and which was actually clearly observed even from the results here that the functionalized carbon nanomaterials worked better than the freshly produced carbon nanomaterials. So as I mentioned earlier, so what we did now is just to see the effect of, for example, pH and dosage on the coagulation process, but also we introduced, we brought in another parameter, which was chemical oxygen demand, because what you notice is the brewery wastewater contains a lot of organic materials. So that's why COD was also measured in this case. And what you see in this figure is, if you were to look at turbidity, actually the turbidity removal reduces as the pH increases, which is actually obvious from the scientific point of view, because at lower pH, the reason why the turbidity removal has been it's high at lower pH is basically because at lower pH you have these hydrogen ions that actually attach on the carbon nanomaterials, and because they are positively charged, then it's easier for them to neutralize the negatively charged materials in the brewery wastewater. And that is the explanation that we used to explain why
Yes, Jeff, we are losing you. Can you hear us? We can't hear you now. Yeah, I think we've lost Jeff there. Yeah, we might have lost Jeff there. And I think, yes, I think the reason for that is load shedding. We have something known as load shedding in South Africa. He will have run out of electricity around this time. But in the interest of time, I really think that we can proceed, because we don't know when he's going to be joining us again. He has a generator, I know. He might be switching over to a generator at the moment, but
he has joined, I think.
He has joined again. Let me see.
Yeah.
Jeff, have you joined? I can't see you from this side. Yeah, I see him here. Jeff, I think you're on mute.
Yeah, I don't know what happened. Let me reshare. I don't know whether you are able to see my screen. Let me just quickly reshare it again.
Okay.
Yeah. Is my screen? Can you see my screen?
Yes, you can see your screen.
Yeah. Okay. Yeah. What I was saying here is we just wanted to see the effect of dosage here on the turbidity removal and also COD removal. But what we see is as we increase the carbon nanotubes, there came a time when actually the turbidity and also COD removal sort of like started going down. Basically, what we concluded here is that this could be because of perhaps there was some sort of interaction between carbon nanotubes other than the carbon nanotube colloidal materials at very high concentration, and this perhaps also is very similar to polymers. coagulants, because polymer coagulants, as you increase the dosage, also you find that the turbidity or even COD removal starts to reduce. So this, we concluded that mechanism for that polymers use, it was the same as our carbon nanomaterials. So the other thing that we also looked at was just to just try to have an idea of the type of mechanism that was used in this coagulation process. In this case, what we had to do initially, because the pH of our water was quite low, it was about 4, but then we sort of adjusted it to about 6.5. But within that pH, the water was still having negatively charged materials with a zeta potential of -25 millivolts. And then in order to test that mechanism, to see what mechanism was used for coagulation, we had to increase the dosages of carbon nanomaterials, and as we increase the carbon nanomaterial dosage, what you see is there was an increase in the zeta potential. What that means is the solution was becoming more positive and so on and so forth, losing its negativity, meaning there was some sort of neutralization of the colloidal materials by the carbon nanomaterials. So in conclusion, what we concluded from this is that the mechanism that is used by carbon nanotubes in this case is basically adsorption and neutralization. So I think what we can conclude here is I think this particular study actually it demonstrated another new application of carbon nanotubes for water treatment. As you saw in my introduction, I talked about nanoadsorbents and nanofilters, but then there's also now an added use of these carbon nanomaterials, which is in the coagulation and flocculation. And then, of course, the removal in terms of the mechanism, we concluded that it was just surface charge neutralization that took place. This study was done many years ago. We have not actually looked at the recommendation that we proposed in the study yet. What we see is in this particular study, the carbon nanotubes actually were not soluble. So we propose perhaps maybe even if we've got researchers who are interested in doing studies on using carbon nanotubes, they can probably investigate the use of soluble carbon nanomaterials to see whether this process works. And also, we only concentrated basically on the use of turbidity. Of course, even COD was used, but I think it's also important to extend the monitoring parameters to other parameters other than turbidity. And what we also see here is we only use the hydrochloric acid to functionalize our carbon nanomaterials. But I think it's important to also look at other chemicals as functionalization media. So these are some of the recommendations that we put up in this study. So I'll wait for some questions during the panel discussion. Thank you.
Okay, thank you very much, Jeff, for that presentation. Yeah, very, very scientific in nature, but I'm sure that at some point you can share with us the typical applications.